Okay, so far we've been looking at KCs, but now we're going to take a look at what's the relationship between KC and KP. If I have an equation that has all gases in it, I can write either a KC or a KP. So here the KC would be simply the concentration of C raised to its coefficient over the concentration of the products raised to their coefficient. Or I could write a KP, which is the pressure of C raised to its coefficient in the balanced equation over the pressure of A times its raised to its coefficient and pressure of B raised to its coefficient. Notice the difference. I have Kc at the top where I talk about concentrations. I have Kp at the bottom where I'm talking about pressures. I use the brackets. When I use brackets, that indicates concentration or molarity or moles per liter. When I am talking about P, I am talking about pressure. And I don't use the brackets, so don't make the mistake of using brackets when you're talking about pressure. Okay, so let's take a look at what the relationship. So I have Kc and I have Kp, and I can actually mathematically determine the relationship between Kc and Kp using the ideal gas law, but we're just going to cut to the chase and go to what that equation will be. And here is the equation. It's Kp, the equilibrium constant for pressure, is equal to Kc times RT, all of which the RT is in parentheses, raised to the power of the change in N. Okay, so Kp is equilibrium constant for pressure, Kc equilibrium constant for concentration, R is the ideal gas law, and that is, we're going to use the one that has liter atmospheres over mole K, which is 0.08206 liters. T is, of course, going to be in Kelvin, and my change in N is the change in number of moles of gas. And if I have a liquid or a solid in that equation, I will not count it because it will not affect the pressure. Okay. Sometimes you need to remember when you're trying to remember the equation, it helps to think about this as the politically correct equation, PC. Okay. So let's go ahead and try doing a problem. So the change in moles, delta N represents the change in number of moles of a gas. So let's take a look at how that would work. So here I have 2 SO2 plus 1, implied 1 O2, becoming 2 SO3. So my change in moles of product minus my change in moles of reactant is going to be this 2, right, minus 2 plus 1, or 3. So my change in N is minus 1. And I can have both positive and negative delta N's, right? Because it's always going to be products minus reactants. Here's another example. I have 1 N2O4 becoming 2 NO2. So my product moles is 2, just the gas, right? Minus 1 mole of gas gives me a delta N of 1. So there are times where Kp will equal Kc, and the time when that's going to happen is when this is equal to 1, and this will be equal to 1 when it is raised, the RT is raised to the power of 0, right? So because anything raised to the 0 is equal to 1. Okay, it's just a common rule of math. So when I have a change in moles is 0, my Kp equals my Kc. Okay, so here's an example of when Kc and Kp are equal. I have 1 mole of H2 plus 1 mole of I2 becoming 2 moles of Hi. So my product moles is 2, my reactant moles is 2. When I subtract them, I get 0. So this whole thing becomes 1, so Kp equals Kc. Okay, let's take a look at a problem. We're going to do this in parts. So we have a container at 800 C filled with NOCl gas, decomposes to form NO gas and chlorine gas. So the first thing you always have to do is write the balanced equation. So first step, you're going to answer the question, which reaction represents this decomposition? So give it a minute, think about it, and then the question box will come up. Okay, so you should have said that it is 2NOCl forms 2NO plus Cl2. Cl is diatomic, and in order to make this balance, the correct equation is 1. Okay, a container at 800 C was filled with NOCl gas, which decomposes to form NO gas and chlorine gas. What is the change in N? Okay, so take a look at the previous equation and answer this question when the box comes up. Okay, so we had 2NOCl becoming N2NO plus Cl2, so we have 3 moles of gas as product, 2 as reactant, so it's 3 minus 2, so our answer is A. Okay, a container at 800 degrees C was filled with NOCl gas, which decomposes to form NO gas, talking about the same equation, and chlorine gas. If the Kp is equal to this, what is Kc? So figure this out, answer the question box when it comes up. Okay, so let's take a look at how we would do that. So we were given the Kp of 1.8 times 10 to the minus 2. We're trying to calculate Kc. Our R is 0.08206. We have to change our 800 degrees Celsius to Kelvin by adding 273, and when we do that, we get 1073. Okay? In order to solve for Kc, I'm going to divide 1.8 times 10 to the minus 2 divided by the product of this, and when I do that, I get Kc, 2 sig figs, is going to be 2.0 times 10 to the minus 4. Okay, we're going to stop there. Okay, we're going to take a look at a Kc-Kp problem. So here we have, if Kc is 13.2 at 30 degrees C, what is Kp for the reaction between 2 sulfur dioxides plus oxygen to give 2 sulfur trioxides? Okay, so our equation, remember it's politically correct, so it's Kp equals Kc times RT, and RT is raised to the change in,